In this video, I'm going to show you how I designed the logic circuit behind my robots. This is actually quite a simple circuit, but I'm excited to show you what we've got. When I was initially designing this robot weeks ago, I had it in my head that the logic circuit was going to be some crazy complicated thing. As I've refined my design over the past couple weeks, I realized the logic can actually be a very simple circuit. In an OR controlled by a microcontroller, the typical approach would be to have a sensor on a servo. When the sensor detects an object, the servo would swing the sensor left and right to measure the distance of objects to either side of the robot. Then, a simple comparison would tell the robot which way it needs to go. While this behavior can be recreated exactly without the use of a microcontroller, it would take up more space than I would like, so I'm going to go with a much simpler approach. Whenever an object is detected, turn to the right. There are some obvious drawbacks to this approach. It can never go in a straight line. It will ultimately always form a giant circle, and right is not always a good direction to go. I haven't tested this robot in a completed state yet, so I can't actually say if this will work at all. However, it should at the very least move, and it should be entertaining. This simplified the circuit down to one single chip, whereas mimicking the microcontroller behavior would require a chip for RAM, it would require a chip for an adder, would require at least one chip to address and read from the RAM. This circuit only needs to know when it needs to turn right. As a result, this circuit is actually significantly easier to build than all the previous circuits I've shown you. The theory is quite simple. Like I said in the previous video, the motor driver we are using gives us a truth table that looks like this. Basically, the motor only turns when the inputs are different. When they are the same, the motor stays still. We don't want them to be the same, so we don't care about those two states. When you reverse the inputs, you reverse the rotation of the motor. Therefore, we need a way to reverse the inputs whenever an object is detected. If you'll remember from our first video, where we designed the sensor circuit, we have an output that will tell us if an object is within a certain range. This is high if we are allowed to go forward, and low if we are not. Now we need to take this one output and turn it into two inputs for the motor. Fortunately, a simple NOT gate will do the trick for us. Since we always want the inputs to be opposite of each other, we can wire the output of the sensor circuit into one of the inputs of the motor circuit and the input of the NOT gates. The output of the NOT gate will wire into the other input of the motor circuit, and just like that, we have a circuit that will reverse the rotation of the motor whenever an object is detected. This will make sense later. The particular chip we are going to use for this is the 74LS04N Hex Inverter. It's called the Hex Inverter because hex means 6, and inverter is simply another name for a NOT gate. Therefore, there are 6 NOT gates in this chip. As you can see, after providing power and ground to the chip, we just need one connection to the input and one connection to the output. It's really a dead simple circuit. To help illustrate this, I'm going to set up the simple circuit just for the Hex Inverter itself. So first I want to connect my power and ground. Next I'm going to choose which two pins I'm going to use. So I'm going to use this input pin, pin 1. And then the output pin will be pin 2. So let's tie this over here. And for the input, I'm going to use a simple push button. I want this default low, so I'm going to add a simple resistor to tie it down to, or pull down resistor. So this ties this to ground by default. Then I add another wire to the other side of the push button. And this goes to our positive voltage. So when I push the button, this pulls it up and gets a logic high. When I let go of the button, it pulls it down and gets a logic low. And to visualize this, we're going to add some LEDs in the correct way. That one's to our input. This one is to our output. Now we're going to connect our ground rails here and our power rails. Now we just need to add power. And now we turn that on. So since our input pin was low by default, our output pin is high, but the moment we press our input or our button for our input pin, they switch. And now our input is high and our output is low. I let go, they switch back. And this is the working principle that we want to work with, because if we want our motors always running, we want one input always high and the other input always low. And if we want to reverse the rotation, we want to switch those. And this is the principle upon which our logic is built. What you are watching here is my assembly of the entire robot that we have designed so far. It is important to note several changes that I have made. The first is to the voltage divider in the sensor circuit. I decided on values for the resistors here. Here's a quick schematic of the voltage divider to explain what is going on. For this divider, I need a voltage range of between 0.5 volt and 3.3 volts. I calculated that I can have the following values. R1 has a value of 3 kiloohms. I didn't have a 3 kiloohm resistor lying around, so I used a 1 kiloohm and a 2 kiloohm resistors in series. R2 has a value of 330 ohms. R3 is the potentiometer, and that has a value of 5 kiloohms. I had a 1 kiloohm potentiometer and a 10 kiloohm potentiometer. So I took the 10 kiloohm potentiometer and put it in parallel with a 10 kiloohm resistor to get 5 kiloohms. Truthfully, R1 is supposed to be about 2.9 kiloohms, and R3 is supposed to be about 5.5 kiloohms, but I rounded. With all that in mind, here's what the voltage divider now looks like. The second thing I changed is I scrapped the 555 timer from the previous video. I still want to be able to adjust the speed of the robot, but I decided that voltage regulation is the better path to go here. This is for 3 reasons. The first is that pulsing the enable pin, although it works, is a technique better suited for a microcontroller, and we are not limited to using a microcontroller here. The second is that although pulsing the enable pin will give you individual control over the speed of the motors, we want the motors to turn at the same speed anyway, so if they're spec'd the same, there's no point in adding separate control. It only adds to the complexity. And the third reason is that although it really wouldn't be noticeable in our project, pulsing the pins does waste some amount of energy because the motors have to ramp back up to speed constantly. This is a problem that's largely avoided when you control the voltage directly. I don't have a voltage controller built in this video, but the next video I will need one, as I plan on running both the control circuitry and the motors off the same power source. Lastly, you'll notice that I am not using the bottom power rail in this video. This is because I want this to be my higher voltage rail. The top rail will be 5 volts and the bottom rail will probably be 9 volts, but that'll be determined later. This circuit took me quite a while to build because I wanted it to look nice and kept messing things up as a result. I actually had to build it twice because the first time there were loose connections somewhere that were throwing everything off. I would say the result was well worth the effort though, as we are presented with this circuit here. In this demo, I'm only hooking up one motor in order to demonstrate how it all works, but I could wire in a second motor and it would still work. I also connected the bottom and top power rails and ran everything off of 5 volts for this. Again, this is a demo. In the final design, those rails will be separate from each other. I couldn't really get the sensor in frame without it wanting to come out of the breadboard, but every time I put my hand over the sensor, the motor changes direction. In addition, the potentiometer allows me to fine-tune the threshold where the motor changes direction. Thank you for watching this video and coming along this journey with me. We're almost done with this robot at this point, and I'm actually really excited to see where it goes. As always, if you got any value out of this, be sure to let me know. Smash that like button, hit subscribe, click the bell to stay notified, and down in the comments let me know what you plan on using hex inverters for in your projects. I would love to see. As always, stay safe, and until next time.